Hi, and welcome to the show. Subscribe at kevinmd.com/podcast and get CME for this episode by clicking on the CME link in the show notes. Today, we welcome back L. Joseph Parker. He's a research physician. Today's KevinMD article is Gene Therapies for Chronic Pain. Joseph, welcome back to the show.
Thank you, sir.
Joseph is a regular guest. Go to kevinmd.com/podcast to search for his prior episodes and hear his story. So let's talk about your most recent article about gene therapies and how it may be used for chronic pain. What's it about?
Well, the gene therapies have really been sort of coming into the forefront. They've been theorized since we started decoding the human genome. And so since the 90s, we've been looking and expecting that at some point we would be able to have gene therapies. But the first few tests didn't go well. The genes, so for gene therapy, you take a gene that's needed and you put it into a virus, which is like a syringe, and it attaches to a specific cell and injects the gene that you wanted instead of its own viral DNA, which has been deactivated. And that gene then, using CRISPR technology, splices itself into the genome. Well, if it randomly splices itself in, that can cause some serious problems. And they had a couple patient deaths, and everything backed off, and they started doing more research, and it slowed things down for about a decade and a half. Now they really seem to have it down. Not only can we understand what different genes do, but we can specifically target a gene to increase its expression or block its expression, or to repair when a defective gene is in place. So with chronic pain, what they were doing was looking for the nerve cells that are responsible for producing hyperalgesia and allodynia and these severe chronic neurogenic pain conditions. And they were going in and suppressing the genes that control the calcium channels. And by doing that, they were turning down the volume on the signals that these neurons produce. And that's one very interesting application. And we know that this technology can work because just recently in China, they cured a type of hereditary deafness in a group of children. And I think 5 out of the 6 children were able to hear within just a matter of days and actually able to start speaking on a telephone. And they did that by replacing a gene that codes for otopharin. And so they put that gene in a viral vector and just put it into the ear. So by liquid, and it gets to the virus finds its way to where it needs to be, injects the corrected gene. And in this case, otopharin is a chemical that allows sound waves or pressure waves to be turned into electrical signals. It's kind of a calcium sensing gene. And once it senses that, it releases the calcium and fires the gene. Without that, you're stone deaf. You can't hear anything. And then, but everything else is all in good working order. So by replacing just that gene, they were able to cure deafness. And of course, in the United States, they have 2 treatments now for sickle cell anemia, where they take bone marrow cells out and they reprogram them. So sickle cell anemia, as you well know, is where you have 2 defective hemoglobin genes. You have 2 sickling genes. Now, having one gives you protection against malaria. So it became a common genetic variant in those areas, and it was protective. Having 2, then your cells will sickle and you suffer horribly. And it's one of the worst conditions I've ever treated, because you have young people who would otherwise be starting to live very active lives in horrible pain as their joints degenerate, their spleen atrophies, and all these things happen. And in the past, all we could do was treat their pain and give them some oxygen and fluid. Now they are actually curing people. And I think this is a fundamental shift in medicine that will be bigger than the antibiotic era, because we will fundamentally be able to not just treat someone to keep them from being sick once they get sick, but we will be able to eventually keep people from becoming sick. So the sickle cell treatments, one uses a lentivirus vector to replace one of the defective sickle cell genes with an adult hemoglobin gene. And it does this in a very amazing way, because that's a big gene. Cuts it in 2, puts it in 2 different pieces, and the gene and the cell knows to combine those 2. The third way is just to activate fetal hemoglobin. When we're in the womb, fetal hemoglobin is expressed so we can hold on to oxygen a little tighter. There's a gene that stops the expression of fetal hemoglobin, and then sickle cell kicks in if we have, two of those genes. Well, they can reactivate the fetal hemoglobin and cure sickle cell that way, because you just need one good functional hemoglobin gene to be fine.
Sure.
And so there's something called Casgevy, which is a treatment to target the BCL11A gene and turn fetal hemoglobin back on. And you look at the applications of this. So what do you think is the medical condition that kills the most Americans every year? And it's a trick question. People will say cancer or diabetes or heart disease and all that, but it's really not. It's simply old age. It is a medical condition. The cells become senescent and we have all these things, but really the difference between a happy old, time as an elderly person and an unhappy one is whether or not you get chronic pain, whether or not you break something. Elderly people fall because their muscles are no longer strong enough to support them. And they break their bones, or sometimes they break their hip bone just turning and then they fall. So quite often they'll break a bone and then fall. They didn't fall and break a bone. I used to see it all the time in the ER. Well, there are genes that code for stronger bones. There's LRP5, SOST, WNT, all of these genes, when activated too much, cause, extremely heavy, dense bones. And they found a family in one of the Scandinavian countries that the guy had been hit by a car and he had no fractures, no bone fractures. And they did x-rays and his bones were extremely dense. And so they looked into it and found that he had one of these mutations that had dramatically strengthened his bones. And our muscles go away if we don't exercise them all the time. But some people are born with a myostatin deficiency. So myostatin is the hormone that makes our muscles go away. If our myostatin gene is defective, we end up heavily muscled without exercising at all. Humans are probably the only animal that has muscles that disappear if you don't work them every 72 hours. And that's because we all went through an evolutionary bottleneck.
Sure.
Our bigger, stronger, and, sort of human ancestor colleagues, the Neanderthals and the Denisovans, they had several times our muscle mass. They had much better bone density. They could have just beaten the heck out of us, but all those muscles needed calories. So when you go through a starvation time, if you don't have myostatin, you can starve to death. Well, humans became very adept at losing muscles and gaining fat, surviving famine. But that doesn't set us up well for old age.
Sure. So before getting into the potential applications when it comes to chronic pain, how widely available currently is gene therapy?
It is amazingly expensive right now. Imagine like $1 million treatment for sickle cell. But if you look at the cost of someone's lifetime treatment for sickle cell, it's a bargain. There are other conditions and other treatments where it's probably, for a while, it's going to be quite expensive. Now, immunotherapy for cancer treatments, that is a type of gene therapy. They take the cells out of the bone marrow cells out, and they sort of train them to detect the cancer cells as foreign objects and then destroy them. And quite often they do that with DNA vaccines. And all of the research that went into the most recent pandemic is going to create a huge number of new therapies and treatments. But it is very expensive, and I don't expect it to go below $100,000 or $150,000.
So in theory, when we apply gene therapies to chronic pain, you gave a little bit about that earlier, people can simply, when you say turn down a volume, simply put, feel less pain. Is that correct?
That's correct. So there are calcium and sodium channels that are specific to pain reporting nerves. So in the periphery, you've got, I think it's NAV 1.7 and 1.8 are the two calcium channels that are specific to the nociceptors, and they report pain in the peripheral nervous system. And that's what lidocaine targets. Lidocaine targets the NAV 1.7. In the central nervous system, you have CAV 2.2, I think, which is a calcium channel. And CAV 2.2 is specific to the second and third order neurons that transmit pain signals on up through the spinal cord into the brain. By targeting NaV 1.8 and CAV 2.2, we can suppress the body's ability to feel pain. An example of this is some people are born with NaV 1.7 or 1.8 mutations, and they can't feel pain at all. They can feel touch, they can feel temperature, but nothing hurts. And that's actually not a good thing because they usually live a short life. They never learn the hot stove lesson.
Sure. Now, what about some ethical considerations? Because this sounds something that you see in a movie, right?
Yeah.
What are the ethical considerations when it comes to the furthering of the applications of gene therapy?
Well, interestingly, one of the first uses of gene therapy in China was done basically illegally or without authorization. A doctor there genetically programmed some children to be immune to HIV. Now, we know that some people are born immune to HIV. We know why, and I think it has to do with the p53 protein. But anyway, p53 receptor on the B cells. He genetically programmed these kids to be immune to HIV. Now, I don't feel that was necessary. There are ways to avoid HIV, and of course, there's treatments for HIV, and plus, you're messing with germline therapy at that point. Now, let's discuss that for a minute. Germline therapy, you are changing the genes in that human being, and they will pass those changes on to their children, right? So, adult gene therapy, you're changing it in me, but it's not changing the gametes, and it's not going to spread onto my children. So very different. So he did go to prison for that. So there are some very serious ethical concerns. And then, of course, if we start treating elderly people with genetic treatments to permanently strengthen their bones and give them more and stronger muscles, will those not be used by young athletes? I would argue probably, but probably not effectively. Young people already have strong bones and muscles that grow when they look at a weight. It's after we get past the age of about 50 that we realize we have to work twice as hard for half the results. And should we deprive an elderly population of a treatment that could give them much happier, maybe not a longer life from accident and injuries and all that, but a better life? Think of the hundreds of billions of dollars that would be saved if elderly people could care for themselves without developing weakness that required nursing homes and full-time care.
It sounds like that there's a little bit of a gray area, or I guess a lot of a gray area between treating a disease like sickle cell and treating a symptom. And there certainly is going to be a huge debate in terms of where we draw that line.
Sure. If you look at muscular dystrophy, they're trying to cure muscular dystrophy with this type of therapy. And one of the ways to do that is to make the muscles stronger so that it overcomes the dystrophic effects. The gene for Duchenne's muscular dystrophy is huge, and they've had problems targeting it. So if they could make the muscles stronger in those kids, then those kids would have a more normal life. At the same time, putting that, someone who wants an athletic child, we already know that in Russia and China, it was state-sponsored, hormone treatment, testosterone treatment, all that stuff, human growth hormone. In the U.S., it's extremely common. It's not state-sponsored, and there's been arguments that, we should have an enhanced Olympics. And the difference between human enhancement and curing a disease or a condition all becomes a matter of perception and opinion, right? I mean, Yao Ming is how tall? And his parents were selected because of their height and athletic skills and basically bred to produce him. Is that fair to all the athletes who have, who would like to have that height and those abilities, but don't have them? Of course, I'm not arguing that that's a smart thing to do. I'm just saying that these things they're already happening. I don't think that we should suppress research and treatment for the elderly and those with severe medical conditions at the same time. We're going to have to work this out beforehand because these things are coming. You could ban it completely in the United States, and it would be in China and Europe in no time, especially China. They are really doing amazing things with this type of therapy. because the state decides everything there. If they decide to go that route, how long before soldiers have muscle fibers more similar to other animals than to humans? I can tell you that humans are the weakest thing on the planet. It's amazing that we're the most dominant species. It's because of the brain. A small chimpanzee is 7 times stronger than an adult 200-pound male, 7 times stronger than me easily. And they're little bitty guys, but their muscle is much, much stronger. It wouldn't be that hard to make that little shift. They are evolutionarily, I think, 98.6% the same as us or something like that. Extremely close. So, will some countries start genetically engineering children so that their soldiers will later have more strength, be able to jump faster and higher? We got to think about these things and make rules now, because I guarantee you it will be happening. Just like they've used methamphetamine was invented by the Nazis to help keep their soldiers up at night and let their pilots fly longer missions.
We're talking to L. Joseph Parker. He's a research physician. Today's KevinMD article is Gene Therapies for Chronic Pain. Joseph, as always, we'll end with some of your take-home messages to the KevinMD audience.
These interventions are coming, and we have to think ahead and work out our protocols and procedures for making sure that they're used responsibly. At the same time, they can dramatically ease the suffering of millions of people around the world. So I don't think that the research should be suppressed.
Joseph, once again, thank you so much for sharing your time and perspective, and thanks again for coming back on the show.
Thank you, sir.